from the definition of elastic curve, and that also depends on the support condition that we investigate earlier with multiple support condition. So now just want to give you some example with the full beam in here, and from what we get it in the textbook chapter 9. For example, if we have a simply supported beam, so one pins and one roller at one end and the other end, and the uniform distributed load, as you can see, the beam will be deflected down, and the red line AB is basically the elastic curve we are talking about, and with the x and y axis defined as shown, then as you can see the whatever at any given point here, that we have that either deflection at that point, and that depends on the how far from the point A. You see the origins, that point located, the deflection will not the same, and it will be changing, as you can see. So start at 1 NA, it's 0 because that the deflection is 0, because that is a roll pins based on our pin at ends support condition we are talking about here, YA equal to 0. And similarly for B, it also roll at one end, so we have the very first support condition, you have delta equal to YA equal 0, in this case B, so you have YB equal to 0. So bottom line, in this case, with simply supported beam, we have YA equal 0, YB equal to 0. The other is the overhanging beam, so there is one overhang from B on the right with the load applied at one end, load P, and the curve will be now curve up here as shown, the line AB, and as you can see, regardless, the support condition that we have is YA equal to 0, deflection at A 0, deflection at B 0. If we have a cantilever beam, then P apply in one free end, and one free end, as you can see, we have the free end on the right, apply in this scenario, delta is, let me correct here, the delta is equal to delta A, and it's non-zero, delta to delta A and non-zero, not equal to 0 because it can move out, right? So that what here, and then we have YA equal to 0, and the slope at point A, theta A, represented by the angle slope of the elastic curve, also equals 0. So those are the example that you will see based on applying the support condition we have. So let's move on to more application of the math to find out the relationship between the moment and curvature. Moment, curvature. So if we have a beam, simply supported beam, one pins, one a roller, and the other again. And if the from the line on the neutral surface, if there are certain load that make the beam changing to have, as you can see here, if the elastic curve is something like the green line, if as the point here, then it's something like this, and then and going up here with certain load that we have. So for example, this one, if you have the load going down here, P1, and the load going up, right? So just example that it will be make the curvature. And what do we have? at this point, if the curvature going down, yes, what we have on this point here, actually it due to the bending moment, and in this case the bending moment is positive because it could create a tension in the bottom and compression on the top. And of course, in this scenario, if deflect up here, then we have a negative moment. So when we see the moment diagram, we can anticipate what is the elastic curve look like with the positive or negative moment. If it's negative moment, it will be a curve up and curve down, as you can see there, because that is how the material, the body behave with the bending moment. And the inflection point, this point we call it inflection point. Let's put IP in inflection point, not internet protocol. What is inflection points? Basically a point on the curvature, the green one, at which a change in the direction of the curvature occurs. So in this case, you can see the change of the elastic curve change that between the two directions due to the positive moment and negative moment. So from that, let me do some definition here. If I cause at certain point, the because it curved, the radius of curvature that divided by rho, then what we have here, let's have rho is spelled at rho, and you can see here, let me write down rho, a Greek. Then in this case, the definition is radius of curvature. This is nothing new to us. When we learn the particle kinematics, we already defined that one. The distance from the center of the curvature to neutral surface of the beam. So by definition, basically, this is the distance from center of curvature to neutral surface of beam. And we define elastic curve. What is the elastic curve? It basically deflects the shape of the neutral surface. By definition, it deflects the shape of neutral surface. So in that case, if we define the just same as the previous one, x here, and the y start from here and always start from the left, so we will have the equation for the elastic curve. We got y, and it depends on the x, the point located on along the beam, and that is the elastic curve function. Elastic curve function. So with that definition, and I showed you previously from the study guide. So let's keep what we have from calculus and study guide of this lesson. I will pull out again the study guide now. So this study guide, and you can see that what study guide for this lesson is, and we have this, the curvature, the degree of curvature here, 1 over rho equal to, yes, And let me write that down here from that equation to our study guide. So we have the degree of curvature, so 1 over rho, and that is degree of curvature equal to dx second derivative of y over x. So it basically the second derivative makes simpler here, and then 1 plus yx first derivative square and overall square root of power 3 over 2. That is the equation we have. And as you can see, we deal with the very small deflection. When it's small deflection, the elastic curve, the green one here, I exaggerate, but it's very close to the green beam, to the yellow, blue beam, which is that the slope is about 0, almost 0, very small. We deal with very small slope of, or very small the angles for the deflection. So what does that mean if we assume small angles? If we assume, and that's normally the case. In the real life, when you deal with the beam, you don't want to have a big deflection. No one wants to live or enjoy in that facility. Angles, so what do we have? If we deal with small angles, then the first derivative, which is the slope, right? So it almost equal to 0. Almost equal to 0. So we can simplify that equation is 1 over rho is equal to yx. Second derivative of the elastic curve, as you can see, because the numerator, the denominator equal to 1. So we have that one here. Okay. So now we will go ahead to determine the relationship between the moment and elastic curve function in the next video.